Hi there. On the bench today, a clamp meter sent in for review by a company called GVDA. I did not pay for it, so I mark it as a promotion, but as you know, that doesn't stop me from giving you an unbiased review. As a start, the box is very generic, no branding and no mentioning of the meter model, which is supposed to be a GD170D. There's a nice enough case, and inside we have the meter with the usual leads and a small crosshead screwdriver for some reason and a thermocouple. Taking the meter out and the case is empty, no manual whatsoever. I mentioned this to GVDA and they sent me a link to download the instructions and specs. You find the link in the video description. The meter is quite heavy but feels nice enough in the hand. Despite the weight, it does not power on. Instead of batteries, the company added the screwdriver for the battery compartment. To be honest, I do prefer using my own batteries instead of some questionable freebies. So let's use that screwdriver for its intended purpose. The lid for the battery compartment is quite flush with the body, so getting hold of it isn't easy, but at least we have a metal-threaded insert for the screw, which is nice. There is space for 3 AAAs. After adding them and closing the battery compartment with its dedicated screwdriver, of course, it's time to turn the meter on for the first time. Nice and very bright display, easy to read, but I wonder how much battery that eats. I will test that, of course. This is not a smart meter, which is a plus in my eyes. There's really no mystery how to operate it. All positions of the rotary switch have a primary function and one or more secondary functions, which you can cycle through with a red func button. The sole exception is inductance, shown as H for Henry, which has no other function. There is one button on the side which serves as the hold function when pressed shortly, or turns the built-in torchlight on or off with long presses. The light is largely blocked by the clamp, but since this is a clamp meter, that is acceptable. Let's have a look inside. 3 self-tappers are visible around the case, but opening these needs a beefier screwdriver than the one that came with it. But it can still play a part in getting the battery compartment open. You don't actually have to remove the batteries, but there is a 4th screw hiding in there next to the metal insert. With that out too, the case can be opened. While battery power is connected to the PCB using springs, there is still a wire to the back shell for the torchlight LED. The circuitry close to the clamp reminds me of the good old UT210E clamp meter I reviewed some time ago. The ALD1994 is probably a dual op amp. The main chip is this SDIC Micro SD78P952 microcontroller. I found only a Chinese datasheet, but it has lots of I/O capabilities, including 2 24-bit ADCs and, interestingly, an LCD driver that seems not to be used because there's another LCD driver on the PCB in form of the TM1729. While we are here, note the print on the PCB, the HK215B, more about that in a moment. The big whitish box is a relay. Below it, you see pretty much all the protection there is, 2 5 meg MELF resistors in series and a PTC below. Typing the name found on the PCB into Google points to the NEOTEK HK215B clamp meter, and clicking on the link showing it on Amazon reveals that my GVDA GD170D and the NEOTEK HK215B are really identical twins. That would explain the nondescript box it came in. Well, regardless of name, let's have a look at the specs. This is from the manual provided by GVDA. The first thing I explained twice to GVDA, but I'm not sure if they understood it, is that this is a 9999 count meter, but the ranges in the manual are all based on 6000 counts. They are obviously wrong, but let's ignore that for now. The DC and AC amp ranges topping out at 1200 amp make it clear that this is a meter more for electricians and installers, not really suitable for electronics. The best resolution of 10 milliamps notwithstanding. In practice, such a low current needs special clamp meters to measure with any accuracy, and the +8 means you have an uncertainty of 80 milliamps even if everything else would be 100% accurate, which it won't. Of note, on AC meters, the meter offers a variable frequency drive or VFD option, which in practice means a low-pass filter. Without that, the bandwidth is specified at 1 kHz. My lab isn't really geared for measuring tens or hundreds of amps, and besides of generating them, the other problem is measuring them in a reliable and trusted way for comparison. With that, I did most of the testing using a setup like this. A coil with exactly 10 windings inside the clamp means any current I send through this coil would register as 10 times the current on the clamp meter. The current passes through a shunt resistor of 5 milliohms, and the voltage drop across this shunt is measured by the BM869S on the right. Every millivolt shown on the BM869S means 0.2 amps of current. In this example, 90 millivolts would be 18 amps, and the clamp should show 180 amps. It shows 187.7, but it's unfortunately just out of the frame. The shunt is only for 15 amps, so I have to keep such tests really short, which means using the hold button on both meters and then turning the current off immediately. After you use your clamp meter to measure large DC amps a few times, you have inevitably magnetized the clamp, which means you see a non-zero value even when no current flows. Clamp meters usually have a rel or zero button to remove that offset, but in the GD170D 60 to 600 amp range, this will cause a problem. I zero the offset and now apply a DC current. The shunt voltage is 49.94 millivolt, which means 9.988 amps, and because of the 10 windings, the GD170D sees 99.88 amps, but it shows only overload. This is a typical problem of rel. When engaging it, it turns auto range off. If I turn rel or zero off and repeat the test, the GD170D correctly switches to the 600 amp range and shows 101.9 amps, which of course now includes the offset caused by the residual magnetism. You can of course subtract it yourself. Another option is to pass a good size AC current through the clamp and slowly lower the current to zero. This is what I'm doing here. The current comes from my recently restored VFD school power supply, which has a convenient variac for this purpose. The other option is to use a degaussing tool, and I have a video about that as well. You may have to repeat the process a few times, but you can get the residual back to zero without needing rel or zero. With my verification limitations in mind, I have no complaints about the current measurements. In fact, the low DC currents were surprisingly accurate and totally usable. For low AC currents below 1 amp, the error increases quickly, and below 0.5 amp is probably not worth bothering. Of note, I did not test VFD in AC amps because high currents with variable frequency are quite tricky to produce. For AC inrush current tests, I use a vintage impedance transformer that converts an input of a few tens of volts AC into tens of amps on the other side. I have used the same method for testing other clamp meters before, so long-time viewers may recognize the method. Here is an example of how this works. I set both meters to inrush mode and then apply a power burst into the transformer. Both meters show roughly the same reading of about 74 amps. By the way, this is more than 60 amps, and according to the manual and the writing on the meter itself, the GD170D should have switched to the 600 amp range, but it did not, because it's a 999 count meter and the quote 60 amp range really goes to 100 amps. The manual and the lettering on the meter should really be updated. Back to the manual. DC and AC voltage states a millivolt range, and it might indeed exist, but the auto-ranging never goes down to it. It is quite common in many meters that switching from volts to millivolts needs a manual input or a different rotary switch position. Since the GD170D has no manual ranging and no millivolt function, the lowest range is the 9.999 volt range. Given that the meter is not targeting electronics, that is okay, but they should stop advertising an unreachable millivolt range. As with current, there is a VFD option, and in addition there is a low Z option. Low Z reduces the input resistance from 10 meg to apparently 300K. This is very useful for electrical installations. If you have a bunch of mains cables running in parallel for some distance, then with a standard multimeter they can all show some voltage, even some of them may actually be disconnected. This quite confusing phantom voltage is induced from the other cables, but the load caused by measuring in low Z mode should kill any phantom voltage readings. As expected, the GD170D struggles severely in low DC millivolt, and is really only usable above 100 millivolts or so. DC volts is much better, and again it's not a 6 volt range but a 9.999 volt range, as it can be clearly seen. The picture for AC volts is similar. VFD mode held a surprise. Initially I thought it's not working. The BM869S is in VFD mode and has no trouble showing 43 volts AC at 50 Hz, but the GD170D shows 0 when enabling VFD. But surprise, surprise, when the voltage is above 50 volts, VFD starts working. I find that quite dangerous. You may probe a voltage in VFD mode and think it's 0, and it could actually be 49 volts. Not necessarily giving you a shock, but you may proceed, say, working on a motor which suddenly springs to life. I reported this significant problem to GVDA, and they are looking into it with the manufacturer, but I have not heard anything further. So how about the low Z mode then? To practice verifying low Z, I use the BM235 on the right. I set the power supply to 5.2 volts DC. The low Z mode in the BM235 does not care whether it's DC or AC, but low Z is not on at the moment. To measure the 5.2 volts, the BM235 draws 0.5 microamps from the power supply. If you divide 5.26 volts by 0.5 microamps, you get 10.5 megohm, which is the input impedance of the BM235. Switching to low Z, and now it measures 5.2 volts while drawing 0.53 microamps, which results in 9.81 megohm. Low Z is obviously not running. The user manual explains that in the BM235, low Z becomes active for voltages greater than 8 volts. So let's test that. It takes a bit to settle, but now it measures 8.4 volts in low Z mode, drawing nearly 100 microamps. If you do the math, the input impedance is now just 84 kilo ohms, a significant drop. I tried the same method with the GD170D, but no matter what voltage, the impedance did not change. Here is 62.8 volts in normal mode, drawing 6.33 microamps, resulting in 9.9 megohm. Engaging low Z mode and nothing changes, so it's still 9.9 megohm. I tested that with voltages beyond 200 volts and it was still the same. For AC, here the GD170D is measuring 304.8 volt AC in low Z mode, drawing 30.92 microamps. Do the math and you get 9.8 megohm, which is not low Z. The folks at GVDA are still investigating, but the results of my voltage tests. With DC volts, you best stay above 100 millivolts because the error increases rapidly below that. Apart from that, accuracy is quite okay, no problems. For AC volts, you do not want to go below 500 millivolts, otherwise accuracy is not bad. Voltages would be fine were it not for the 50 volts VFD dead zone and the fact that low Z doesn't work at all. The bandwidth with VFD not in use is actually better than the spec. The 3 dB point is at 5 kHz. The resistance range starts at 600, but in reality 1000 ohm, which is quite high. I expect issues in the very low ohm ranges, rel notwithstanding, and the top should go to 99 meg instead of 60. Continuity is beeping below 50 ohm. It probably does, I have not tested that. As predicted, the accuracy below 10 ohm is not great, but just good enough for rough ballpark numbers. From 100 ohm onwards, accuracy is quite good. The error starts increasing again towards the end, but that's mainly the result of having just 4 digits for very large numbers. It is still quite usable and goes all the way to 99 meg ohm. Onwards to continuity, of course with the leads that were included. These are the usual PVC probes, nothing special about them. And they perform terribly. The GD170D beeps, of course, and there is a light just below the clamp that lights red. To answer the question whether the miserable performance is the problem of the meter or the probes, I changed them out to better ones. These happen to be Pomona probes, but other brands are available. And it's very clear that the problem are the budget probes that came with the GD170D. A common issue, I always recommend replacing the cheap probes that come with most meters. But I guess they will be good enough for diode test. No issue with one diode or 2 in series. A red LED lights and the forward voltage is shown. 2 red LED light just about and no voltage is shown. A yellow LED lights and the voltage is shown. A white LED lights and surprisingly the voltage is shown. 2 white LEDs do not light and no voltage. Capacitance and inductance do not follow the 660-600 pattern. The accuracy spec for capacitance is not particularly impressive, but would be okay for electrical use. I skip frequency and temperature. The last thing we look at is inductance, a function that is not often found in multimeters. Moreover, this implementation has quite impressive accuracy claims. The note of the upgraded version probably reflects the fact that GVDA has 4 versions of the GD170, presumably A, B, C and D, and only the D version has the inductance. My test results on capacitance are quite standard. There is the expected jump when going to electrolytic caps, but otherwise an okay performance. The inductance is pretty good up to 1 millihenry, and then the error is a bit larger than expected. Something weird is happening at 9 millihenry, and then it works again up to 1 henry, which is the largest value I tested. Here is the meter measuring 8 millihenry. I connected a scope in parallel and the frequency is 10 kHz. When I switch to 9 millihenry, watch the meter. It briefly displays 9 point something and then drops to a nonsensical 0.06 or thereabout. The frequency is still 10 kHz. There's some bouncing around on the scope before the meter and scope settle on the new but false value. Moving on to 10 millihenry causes a major change. I need to adjust the scope because the level has dropped so much the scope now triggers on a periodic spike, which I assume indicates the measurement cycle of the GD170D. When the scope is finally adjusted, it is clear that the test frequency is now 1 kHz and the meter shows the 10 millihenry reasonably accurate. It's not a problem with the 9 millihenry setting of my inductance decade because other LCR meters measure it just fine, for example the Zoe ZT-MD2. I reported this problem to GVDA as well, but nothing back so far. I skip showing NCV and live. They work, and this video is way longer than I intended and possibly deserving by the GD170D, but one thing I really wanted to know is how much does this display cost in battery life? The short answer is a lot. More than 32 milliamps, sometimes close to 40 milliamps is crazy. No wonder my AAA batteries are already nearly exhausted after a couple of hours testing the GD170D. The beeper drives it to 80 milliamps using the torch, and it's about 46 milliamps. The GD170D has no special low battery warning. Instead, the battery state is always shown and the state is indicated by how much it is filled. it becomes empty at 3.3 volts, and that's the point when you should definitely replace them, because the meter will keep going for a while longer but showing false values. So what's my conclusion? I think this meter has a few big problems. Top of my list is the VFD 50 volts dead zone, because that is a safety issue. That low Z is not working is weird and disappointing, but not a safety issue. Add to this the horrendous battery life. Sorry GVDA, but as it stands I can only say don't buy, even though its basic functions are fine. I would really like to know if the twin meter, the NEOTEK HK215B, has the same issues, or if anyone found the same issues I did on the GD170D. I searched the internet, but to no avail. Does this mean just my sample was faulty and all the others out there are fine? Or did nobody else bother to test things properly? I leave it to you to judge. If you like my videos, don't forget to like and subscribe and help growing this channel, and consider becoming a Patreon. The link's in the description. Thanks for watching.